In this second episode of the video lesson series on the laws of thermodynamics, we will start studying the second law of thermodynamics. As you can see, you are expected to demonstrate higher order learning for this section. State the second law of thermodynamics, apply the second law of thermodynamics to engineering devices and systems, evaluate the performance and evaluate the validity of a given thermodynamic systems, and suggest improvement or improve the performance of systems and processes. And this lesson supports you partially achieving the learning outcomes 1, 2, 3 and 7 of this module. The first law introduces the fact that energy is a conserved property. That means the total quantity of energy is a constant. However, the first law fails to comprehensively cover the complete behavioral spectrum of energy. For example, the first law does not emphasize the direction of heat transfer. We all know by experience that if a hot cup of a tea kept on a cooler surrounding will not get even hotter by absorbing heat from the cooler surrounding. That means heat will not flow from a cooler body to a hotter body by its own. The first law of thermodynamics does not prevent heat transfer from cooler body to a hotter body. For example, imagine a hypothetical process where a 100 milliliter cup of a tea at 80 degrees Celsius absorb 500 joules of heat from its surrounding. Surrounding is at the room temperature. Since the heat transfer by the surrounding is 500 joule and the heat transfer or heat absorbed by the cup of tea is also 500 joules, there's no loss of energy. That means this process satisfies the first law of thermodynamics. But we know by experience this process will never happen in the real world because hot cup of a tea will not get even hotter by absorbing heat from a cooler surrounding. This is a significant gap in the first law of thermodynamics, and the second law fills this gap by introducing a directionality to heat transfer. It establishes that heat will not flow from a cooler body to hotter body by its own. By re-emphasizing the phrase by its own, let me put forward you a question to think. If heat does not flow from a cooler body to a hotter body, how does the refrigerator or air conditioner work? You know your domestic refrigerator, you have a refrigerant compartment where you put food, maybe ice cream, where your refrigerator is kept in room temperature, maybe in your dining area or in the kitchen, and it is supposed to transfer heat from the cooler refrigerant environment to the surrounding. The situation for an air conditioner is also same. Imagine if you fixed an air conditioner in a classroom, air conditioner is required to transfer heat from the classroom to the surrounding. You are maintaining the classroom temperature, let's say 23 degrees Celsius, whereas surrounding temperature may be 28 to 30 degrees Celsius. So heat flows from a cooler body to a hotter body in a refrigerator or air conditioner. Then how does it happen if heat is not allowed to flow from a cooler body to a hotter body? I'll give you 10 seconds to think about it. If you still cannot figure out, just think what will happen in a power cut. Will you be able to run your refrigerator or the air conditioner? That gives you the hint. So you need to have work input. Only by means of a work input, heat flows from a cooler body to a hotter body. We will study this in detail later. The directionality introduced by the second law of thermodynamics is not confined to direct heat transfer. It is applicable to all types of energy interactions. For example, certain chemical reactions takes place only in one particular direction. Another example, an inflated tire releases air to the surrounding in case of a puncture. It's not surrounding air coming into the inflated tire. While the first law focuses on the quantity of energy, the second law introduces the concept of quality of energy as well. Therefore, quantity of energy alone is not sufficient. It must be of high quality to produce a decent work output. Using the concepts of the second law of thermodynamics, we will investigate heat engines, heat pumps, refrigerators, and air conditioners. In fact, the second law of thermodynamics establishes the theoretical limits of performance of these devices. This is a heat engine, this is a heat pump, this is a refrigerator, and this is an air conditioner. Heat pumps, refrigerators, and air conditioners transfer heat from a cooler body to a hotter body by means of a work input. And heat engines are devices that produce work from heat energy. All these devices operate between things called thermal reservoirs. Therefore, let us first learn the concept of thermal reservoir. A thermal reservoir or heat reservoir is a device or is a body that can either absorb or supply heat at constant temperature. Therefore, a thermal reservoir is an isothermal heat transfer device. It either absorbs or supply heat in an isothermal process. When it absorbs heat, we call it a heat sink. When it supplies heat, we call it a heat source. Maintaining the temperature constant could either be done artificially through a control circuit, like in a boiler, or it could be a natural phenomenon. We can consider ocean or large lakes or rivers as thermal reservoirs because of its large thermal mass. Because you can supply or you can absorb huge amount of heat without any substantial change of the temperature because it has a greater thermal mass. For example, even if this power plant dumps its condensers rejected heat into this lake in very large quantities, due to the large thermal mass of the lake, there's hardly any temperature change. Therefore, this lake is a thermal sink. It absorbs large quantity of thermal energy or large quantity of heat without changing in temperature. Also, when we consider this multimedia projector placed in a classroom and the amount of heat the projector rejects to the atmosphere, we can consider the air in the classroom also as a thermal reservoir, because the projector does not heat up the classroom. So these are examples of natural thermal reservoirs. On the other hand, this boiler is made to be a thermal reservoir through careful control of the temperature. So the temperature is artificially controlled here. However, since heat transfer takes place at constant temperature, this is also a thermal reservoir. With that introductory note, let's go to explore the second law of thermodynamics. There are different ways the second law is expressed. Two common ways are the Kelvin-Planck statement and the Clausius statements that we are going to learn shortly. Also, there are several corollaries of the second law of thermodynamics covering different aspects, such as reversible heat engines, thermodynamic temperature scale, the property entropy, and the principle of increased entropy. We will explore them gradually. The Kelvin-Planck statement is concerned about heat engines and the performance constraint of heat engines. It says it is impossible for any device that operates on a cycle means a thermodynamic cycle, to exchange heat with just a single reservoir and produce a net amount of work. This is a very important statement of the second law, which tells us why the efficiency of a heat engine cannot reach 100%. Schematically, we can represent this statement like this. There's a reservoir and there's a heat engine. It absorbs QH quantity of heat and then produce work output which is equal to the QH amount of heat. So therefore theoretical efficiency becomes 100% because this device fully converts the heat energy into work. But the second law says this type of an engine is impossible. If there's a heat engine, it must exchange heat with two reservoirs at least, hot reservoir and cold reservoir. You extract QH amount of heat from the hot reservoir and you have to transfer QL quantity of heat into the cold reservoir. This is essential. Without this, you cannot run a heat engine cycle. That's what the Kelvin-Planck statement says. Therefore, since part of the heat energy is released to the environment without converting into work, even in an extremely theoretical case, the efficiency of the heat engine cannot be 100%. It must be less than 100%. You must clearly understand this QL is not due to insufficient or inefficient insulations. Even if you have a perfect insulation, still you have to have a mechanism to reject this QL amount of heat to a cold reservoir. In fact, you have to spend money to build devices which are capable of releasing this QL amount of heat to the cold reservoir. This is an intentional or deliberate heat rejection which is required in order for the heat engine to operate in a thermodynamic cycle. You have to clearly understand this is a deliberate heat transfer. It is not heat loss due to improper insulation. We can understand the necessity of that deliberate heat rejection from this simple example. Consider this simple piston cylinder device. If you expand the gas inside the cylinder, you can get some work from the moving piston. To do that, you have to supply heat into the cylinder. Once you heat up the gas inside the cylinder, consequently, as the gas expands, piston moves forward and thereby you can get some work done. Once the piston is fully extracted, the work done completes. If you want to keep doing work, you have to keep the piston motion in a cyclic manner. Therefore, to start the second cycle of piston work, you must bring it to the original position. The only way to bring the piston back to the initial position while producing a net work output from this device is just letting the air inside the piston to cool down until its volume drops. Cooling down means rejecting heat to the surrounding. Then your piston will come back to the initial position. Therefore, without making this deliberate heat rejection, you cannot bring the piston back and if you cannot bring the piston back, you cannot continue producing work output from this simple heat engine. Therefore, you can understand that heat rejection is an essential requirement for a heat engine to operate in a thermodynamic cycle. With this knowledge, I think now you can understand the need of this big cooling tower in a thermal power plant. These cooling towers cool the condenser cooling water to help rejecting heat. Perhaps you may have this question: cooling towers in a thermal power plant is an utter waste of energy and money. Answer is yes, but as we just learned, we have no option other than that purposeful heat rejection. You can see, in order to construct these cooling towers and condensers, etc., it costs a lot of money. So you are spending money to waste energy, but we have no option because it is a requirement, which is explained by the Kelvin-Planck statement of the second law. After having learned the performance constraints of heat engine, let us now investigate the heat engine cycle. Probably the best living example for a heat engine cycle is the steam power plant that you see in this picture. That comprises of 4 key elements. Number 1 is the boiler, which supply heat to produce steam, and then steam turbine, which converts the thermal energy of steam into a work output, and the condenser, which is the device which is responsible for the deliberate heat transfer to the cooler surrounding or the cold reservoir. And then we have a feed water pump. Schematically, a heat engine cycle can be shown like this. This is a boiler where heat is supplied to the working fluid, and this is the turbine where work is produced from the heat energy, and this is a condenser where heat is rejected to the cooler reservoir, and this is the feed water pump, which increases the pressure of the feed water to the boiler pressure. We can derive an equation for the thermal efficiency of a heat engine cycle. The generic thermal efficiency or generic efficiency equation is the desired work output or the desired output divided by the input you are providing in order to get that output. We can derive an equation for the thermal efficiency like this. In generic terms, efficiency is the desired output divided by the input we provide to get that output. In this heat engine cycle, the desired output is the work output. Of course, it is the net work output of the heat engine cycle. And Q in is the heat input in order to get that work output. Q in is in fact QH, that is the heat input. By applying the first law of thermodynamics, now you know how to draw the system boundary. So you can draw an appropriate system boundary, and then you will find out by applying the first law of thermodynamics that work output is equal QH minus QL. Therefore, you will end up with this equation. Thermal efficiency is 1 minus heat transfer to a cooler reservoir divided by the heat transfer from the hot reservoir. From the second law of thermodynamics, we know that we can't have a thermodynamic cycle or heat engine cycle having QL equals to 0. Because QL cannot be 0, you cannot achieve 100% thermal efficiency even in a theoretical scenario. Carnot principle is a corollary of the second law of thermodynamics. It says the efficiency of a reversible heat engine operating between two thermal reservoirs is always greater than the efficiency of an irreversible heat engine operating between the same two thermal reservoirs. We can examine this further from this schematic diagram. You know, heat engine is required to operate between two thermal reservoirs. Here the hot reservoir, this is a cold reservoir. This is an irreversible heat engine which absorbs QH quantity of heat from the hot reservoir and reject QL quantity of heat to a cold reservoir and produces W out irreversible quantity of work. And this is a reversible heat engine. Carnot principle says the efficiency of this reversible heat engine is always greater than the efficiency of the irreversible heat engine which is operating between the same two thermal reservoirs. Consequently, the work output of the reversible heat engine is greater than the work output of the irreversible heat engine. Reversible heat engines are called as Carnot engines as well because that comes from the Carnot principle. And there's a corollary of the Carnot principle which is itself a corollary of the second law as well. All reversible heat engines operating between the same two thermal reservoirs have the same efficiency. Of course, there's no need to derive this one. This is a very obvious one from the Carnot principle because reversible heat engine is having the greatest efficiency. Therefore, you can't have anything which has a greater efficiency than a reversible heat engine. So if you have n number of heat engines, reversible heat engines, their efficiency must be the greatest. So their efficiency then must be equal. Since we learned the Carnot cycle, let us examine its processes. It has four processes because it has four key elements. At the boiler, you have reversible isothermal heat addition. If it is not a Carnot heat engine, it is only isothermal heat addition. But since it is a reversible or Carnot engine, it is reversible isothermal heat addition. Through the turbine, you have reversible adiabatic expansion. If it is not a reversible cycle, then it is only adiabatic expansion. Through the condenser, you have reversible isothermal heat rejection. Through the pump or the compressor, you have reversible adiabatic compression. The term reversible adiabatic is equivalent to isentropic. That means there's no change of entropy. Once we learn the concept of entropy in the next lesson, you will better understand this. But for the time being, remember the fact that reversible adiabatic means isentropic. That means there's no change of entropy through isentropic processes or reversible adiabatic process. This is another addition to thermodynamic processes that we have already learned. We have learned adiabatic processes, polytropic processes, isochoric processes, isothermal processes, so and so. Now this is isentropic process. An isentropic process is a process where entropy does not change across this process. Heat pumps, refrigerators and air conditioners. We know that heat engines are devices that produce a work output while transferring heat from a hotter body to a cooler body. These devices, that is heat pumps, refrigerators or air conditioners, are devices that transfer heat from a cooler body to a hotter body with the aid of a work input. Actually, refrigerators and air conditioners are put into one category called refrigerator because air conditioner is type of a refrigerator, but heat pump is different. Therefore, we study heat pumps and refrigerators separately. You can see heat pumps, refrigerators and air conditioners are reversed heat engines. Look at this schematic diagram of a heat engine. Imagine if you reverse all these processes. That means you reverse the direction of the work transfer, you reverse the direction of the heat transfer. Then you will get this type of a system. This is exactly what heat pump or refrigerator does. It transfers heat from a cooler body to a hotter body by means of a work input. Therefore, reverse heat engine cycle is the refrigeration or heat pump cycle. But components are totally different. While the Kelvin-Planck statement establishes the operational constraints of heat engines, Clausius' statement of the second law establishes the operational constraints of heat pumps and refrigerators or air conditioners. It says it is impossible to construct a system which will transfer heat from a cooler body to a hotter body without work being done on the system by the surrounding. In other words, what it tells is heat will not flow from a cooler body to a hotter body without a work being done on the system. Schematically, this type of a system is impossible. This heat pump or refrigerator transfers heat from a cooler body to a hotter body by its own. It's like hot cup of a tea is getting even hotter by absorbing heat from a cooler surrounding, which is not possible. In order for heat to flow from a cooler body to a hotter body, there must be a work done on the system. This is what the Clausius statement says. Let's now try to derive an equation for the performance of heat pumps and refrigerators or air conditioners. Before deriving an equation, we need to identify the characteristics difference between heat pump and refrigerators, which makes us to consider heat pumps and refrigerators or air conditioners differently. Fundamentally, both devices pump heat from a cooler body to a hotter body. However, their objectives are different. If you look at a refrigerator, the objective of a refrigerator is to cool an environment by pumping heat out from the environment concerned. For example, if you take your domestic refrigerator, the purpose is, or the objective of the refrigerator is to keep your refrigerated compartment at a low temperature. If you take an air conditioner, again, the objective is to keep the air conditioned space at a low temperature. Therefore, our concern is the quantity of heat taken away from the cooler environment. We are not bothered the quantity of heat supplied to the hotter environment. On the other hand, if you take a heat pump, the objective of the heat pump is to heat up an environment by pumping heat into the environment concerned. So you extract heat from a cooler body and pump it to a hotter body. In that application, we don't care what is the quantity of heat absorbed from the cooler body. Our concern is, our focus is the quantity of heat supplied to the hotter body. Therefore, although heat pumps and refrigerators are transferring heat from a cooler body to a hotter body, their objectives are different. When we are analyzing the performance, we are using a term called coefficient of performance instead of efficiency. The reason is the coefficient of performance is always greater than unity. That is, it is always greater than 100%. Our general understanding about the efficiency is it must be less than 100%. To avoid any ambiguity, we use the term coefficient of performance therefore. Let us consider this heat pump or refrigerator. So imagine it is a heat pump. The general equation for performance is desired output divided by the input given in order to take that output. When you take a heat pump, desired output is QH because that is our focus. In order to get QH, you are supplying W in. Again, by applying the first law of thermodynamics and defining the system boundary correctly, you can find that W in is equal QH minus QL. Therefore, the coefficient of performance of a heat pump comes 1 over 1 minus QL over QH. When we consider a refrigerator, then our desired output is QL because our objective is to cool the environment. Therefore, our focus is getting heat rejected from the cooler environment. In order to get that done, we are supplying W in input. Therefore, coefficient of performance of refrigerator is QL over W in. Again, by applying the first law of thermodynamics, you can find W in is equal QH minus QL. Consequently, the coefficient of performance of a refrigerator becomes 1 over QH over QL minus 1. These two are the coefficient of performance equation for heat pumps and refrigerators. Refrigerators means it includes air conditioners as well. Before moving forward, to refresh yourself, try this quiz. Derive a relationship between coefficient of performance of a heat pump and refrigerator. You know the two equations and derive an equation for a relationship between COP HP and COP ref. Pause this video and try this exercise. Attempts to measure the hotness and coldness that now we know as the temperature is dated back to a number of centuries. There had been several successful efforts in developing temperature scales. Fahrenheit scales and Celsius scales are the two such commonly used scales even by today. However, the curiosity to explore the absolute zero or the coldest point that one can theoretically achieve is said to be influenced by the reversible heat engine or the Carnot heat engine that we have already learned. Lord Kelvin has played a vital role in developing this thermodynamic temperature scale. If you recall the Carnot principle, its corollary says all reversible heat engines operating between the same two thermal reservoirs have the same efficiency. Let us lead to identify a very important characteristics of reversible heat engines. Let us consider these two reversible heat engines operating between the same two thermal reservoirs. The first heat engine is absorbing QH1 quantity of heat from the hot reservoir and reject QL1 quantity of heat to the cooler reservoir and provide W1 work output. Whereas heat engine 2 absorb QH2 amount from the hot reservoir, reject QL2 to the cold reservoir and produces W2 work output. Since both of these are reversible heat engines, from the Carnot principles, we know that thermal efficiency of the first heat engine is identical to the thermal efficiency of the second heat engine. If you look at the efficiency equations, you can see it is independent of the properties of the working fluid. It solely depends on the temperature of the hot and cold reservoirs. Because that's what the Carnot principle says. The efficiency, the two efficiencies are identical. That implies the ratio QL over QH is a function of TH and TL. We can show that, although I'm not going to derive it here, we can show that this function further simplifies as is a ratio of the function of temperature TL and the function of temperature TL. Lord Kelvin proposed the function is simply the temperature in absolute temperature scale, that is in Kelvin scale. Therefore, we get the result QL over QH is equal TL over TH when temperature TL and TH are expressed in kelvins. This result is very important for us. This is valid only for reversible heat engines. Therefore, if you have a reversible heat engine or Carnot heat engine, you can easily replace the ratio QL over QH by TL over TH. With this knowledge, let's try to investigate the performance of Carnot cycle. If this is a Carnot heat engine, then we know the ratio QL over QH can be expressed as TL over TH. Therefore, we get the equation reversible thermal efficiency of a heat engine is 1 minus TL over TH. It's very important to remember that temperatures must be expressed in kelvins, not degrees Celsius or not in Fahrenheit. Here you can see when the temperature of the hot reservoir increases, efficiency increases, or when the temperature of the cold reservoir decreases, again efficiency increases. However, you can't have very high temperatures for hot reservoir because it is a material constraint. For example, if you take a steam power plant, usually the hot reservoir temperature or the steam temperature is about 550 degrees Celsius. Cold reservoir, on the other hand, is constrained by the room temperature because we are taking either seawater or river water or water from a tank to cool the condenser cooling fluid. Therefore, temperature of the sea or the river or the tank, which is the room temperature, determines what is the lowest temperature, TL. However, even in practical systems, as the hot reservoir temperature increases and cold reservoir temperature decreases, efficiency of the heat engine increases. You must remember, this equation can be applied only for reversible heat engines, and this is the greatest efficiency a heat engine can produce. We already know that if we reverse the directions of heat and work transfer in a heat engine, we are getting heat pump or refrigerator. Therefore, if we reverse a Carnot heat engine cycle, that is a reversible heat engine cycle, we are getting the reverse Carnot cycle or the Carnot heat pump or refrigeration cycle, which is a reversible cycle. So as long as it is a reversible one, then we can apply that heat transfer ratio is equal to the temperature ratio of the two reservoirs. Therefore, we will get new equations for the coefficient of performance under reversible operation. This is the coefficient of performance of a heat pump under normal operation, and this is the same for a refrigerator under normal operation. And if it is operating in a reversible manner, that is a reverse Carnot cycle, then the heat transfer ratio can be replaced by the temperature ratio. Therefore, coefficient of performance of a heat pump when it is operating in a reversible manner can be expressed like this. Similarly, coefficient of performance of a refrigerator in the reversible manner we can express using this equation. So in this lesson, we learned several new things: the second law statements, like the Kelvin-Planck statement and the Clausius statement, and also we learned about heat pumps, refrigerators, air conditioners and heat engines. And Carnot principle, we learned about the coefficient of performance of refrigerators and air conditioners, how it differs from efficiency concept and the efficiency of a heat engine and reversible heat engines, which are known as the Carnot engines. So we learned quite a lot of things. You can replay this video as many times as you want until you fully understand the concepts. And there are formative questions on Moodle together with this muddiest point question. In the muddiest point questions, you have to list 3 most confusing concepts that you learned in this lesson. As usual, you must submit your answer at least 4 hours before the lecture so that we can discuss your problems in the lecture. During the lecture, we'll try a couple of additional questions, as well as I will be happy to answer any of the special questions that you have from this lesson. Thank you.